All right, so welcome everyone to NOSSDAV 2020. So I am Lucille Satelli of Université Nice Côte d'Azur in France, and with my colleague Jong-Sok Lee of Yonsei University in Korea. We are very proud to be the TPC chairs of this 30th edition of NOSSDAV, and our general chair is Reha Sivanla. So NOSSDAV has a long tradition of being an interactive and discussion-oriented workshop, which gathers researchers, students, practitioners, developers, both from academia and industries, to discuss next generations, next directions in networking, multimedia application, operating systems, and other related areas. So this year is a bit special because it's the 30th anniversary of NOSSDAV, predating ACM Multimedia by 3 years. So it's quite a long tradition workshop. So we were supposed, of course, to have nice celebrations, but unfortunately, this will have to wait for next year. However, we were still able to put together, I hope, an interesting and an exciting program. So despite the harsh conditions at the time of the submission, we were very happy to have 20 submissions to NOSSDAV this year, out of which 10 articles got accepted. That corresponds to a 45% acceptance rate. We got submissions from a wide range of countries, to name a few: Australia, China, Finland, Germany, Spain, UK, the US. And the topics were also quite broad. So we had, of course, papers on adaptive streaming, but specifically papers on low latency streaming, SDN. We also got deep reinforcement learning, as we just heard about by our keynote speaker. So DRL applied both to regular video streaming and immersive content streaming, specifically 360-degree video streaming, and we'll have also other types of immersive content like point cloud streaming. So stick around because this is a very interesting program and 2 sessions that we are going to have. All right, so we'll have 2 sessions then. So the first session will be chaired by Jong-Sok. So we'll have 5 papers in both sessions, in each session, so 10 papers in total. You have here the NOSSDAV #1, so NOSSDAV #1 session in Slido. This is the tag that you need to find in order to post questions on the papers. And then the papers have their corresponding numbers, so you just have to select the corresponding tag. So the first session will be on adaptive streaming. So we'll have different types of papers on wireless, on reinforcement learning, CMAF, on live streaming, and on QoE. And then the next session, session number 2, will be on immersive media. So 360 video streaming, also a bit of wireless and point cloud. Okay, so the organization, the way it's going to go is quite, well, you're quite used to it now. We have 30 minutes per session with 5 papers in each session. So the first, we've decided to have the first 15 minutes dedicated to have a bunch of elevator speech from the authors, from the presenters, for all the papers. During these first 15 minutes, the attendees are very, very welcome and expected to have more time to post questions on Slido for every papers. And then after these 15 minutes, the last 15 minutes will be dedicated to the Q&A session for every papers in the order of appearance. Okay, so let's now start with the first session, which is going to be chaired by Jong-Sok. So Jong-Sok, if you want to take over screen sharing.
Thank you, Lucille. So Okay, let me take the screen. Okay, so as Lucille just mentioned, so we have 5 papers in the first session of NOSSDAV. So here is a list of the papers, and now I like to invite the authors to make an elevator speech, like 2 to 3 minutes. So first paper is entitled Self-Play Reinforcement Learning for Video Transmission by which is going to be presented by Tianqi Huang from Tsinghua University. Tianqi, please unmute yourself and then make a short summary of your paper, please.
Hello, everyone. Can you hear me?
Yes.
Let me start the video. Wait a minute. Stay tuned. Something like that. Hi, everyone. Hi, everyone. I'm Tianqi Huang from Tsinghua University, and thanks to my advisor Li Fengsen for his outstanding presentation. Okay, and here I'm glad to introduce our paper, Self-Play Reinforcement Learning for Video Transmission. So video transmission services often adopt adaptive algorithms to ensure users' demands. For example, we use adaptive bitrate algorithm for we call ABR to achieve higher bitrates and lower buffering. And existing technologies are often optimized and evaluated by the function on the goal that linearly combines several weighted matrices. While we find that the matrix for each matrix requires to be carefully designed, and sometimes the given function fails to describe the requirement accurately. So we propose a novel self-play reinforcement learning-based system called SWI, aiming to update the policy by utilizing the actual requirement. For example, we assume that the requirement in the ABR scenario is first, avoid rebuffering, and next, we can achieve higher video bitrate. So the key idea of SWI is to generate the strategy that meets the requirement under the assigned network environment as much as possible, where the network environment is composed of a number of network traces. Here, we treat the learning process as a competition between 2 trajectories. In detail, SWI first samples several trajectories from the same starting point. Then it estimates which trajectory is closer to the original requirement. Finally, the neural network will be optimized via increasing the probabilities of the swing samples and reducing the probabilities of the value samples. So to build SWI, we develop simulation environments, design adequate neural network modules, and invent training methodologies for dealing with different requirements on various video transmission scenarios. We evaluate SWI on 2 tasks, such as adaptive video streaming and cross-source live streaming. Trace-driven analysis demonstrates that SWI optimizes itself according to the assigned requirement faithfully and outperforms state-of-the-art methods. For more details, please refer to our paper, Self-Play Reinforcement Learning for Video Transmission. Please feel free to let me know if you have any questions. And one more thing, we have open sourced our project in our lab's GitHub homepage. Thank you.
Thank you, Tianqi. Okay, now next paper is FALCON, Joint Fair Airtime Allocation and Rate Control for Dash Video Streaming in Software-Defined Wireless Networks, which is going to be presented by Miguel from I2CAT Foundation. Miguel, please.
Hi, do you hear me?
Yes.
Okay, hi everyone. This is Miguel Catalan from I2CAT Foundation, which is a research center located in Barcelona, Spain. Okay, so the paper FALCON with this long title The main objective of FALCON is basically to improve dash video streaming performance in wireless dense scenarios. These scenarios are very challenging due to the increase of congestion caused by the high amount of clients competing for the shared resources in an uncontrolled and unbalanced way. And this impacts for instance, the on-off behavior of the dash clients, the resource estimation of the ABR strategies, and this leads to an unfair and degraded quality of experience. So what we have designed, or what we have targeted, is 2 ways of improving performance in Wi-Fi networks by considering network assistance. At the dash service side, we focus on video rate recommendation following the SAN specification. And at the wireless side, we focus on centralized association control to properly balance users among the available access points. We have joined these 2 functionalities in a novel algorithm which tries to optimize proportional fairness in the network and according to the airtime consumption of the dash clients. So in order to evaluate this solution, what we have done is to simulate an airplane entertainment system, which is an interesting example of ultra-dense scenario with a lot of clients competing for the wireless resources. And we evaluated FALCON working together with 3 referent adaptive bitrate strategies: Panda, Bola, and Robust MPC. And what we saw here is that FALCON provides significant benefits by minimizing instability and buffer underruns for all the ABRs and all the cases, especially when increasing the number of users and the congestion. And it also obtained a fair video rate and airtime allocation among the clients. So we were able to enhance the utilization of the network resources and also to contribute to an enhanced quality of experience. And okay, this was a simulated scenario. Now, as our future work or present work indeed, we are working on a real implementation using Dash.js, a RAN controller, some single board computers as access points, Prometheus for the telemetry, and etc. So we are starting to implement and have real results of this solution. And okay, that's more or less all. Thank you.
Thank you. The third paper is evaluation of CMAF in live streaming scenarios, which will be presented by Thomas from Lancaster University. Thomas, please.
Hello, can you hear me?
Yes.
Right. So my name is Thomas Lyko, and I'm a PhD student at Lancaster University. And I'm here to present my work, the evaluation of CMAF on live streaming scenarios. In this paper, we have evaluated the impact of the common media application format on ABR performance in various live streaming scenarios. We have tested 4 popular ABRs across 16 latency settings, using 7,000 throughput traces based on CDN logs of a live commercial TV service. We have developed a simulation model to allow for such extensive evaluation. We have verified our simulation model against the Dash.js player. We have presented the ABR performance using multiple metrics, including the P1203, the QoE model, which combines all QoE factors into a single value. We have found that CMAF can significantly improve ABR performance, especially at the lowest latency settings, where we have observed a 43 to 71% reduction in sessions experiencing rebuffering. However, we have also found that the performance improvement was not universal across all ABRs tested, which indicates that ABRs should take into account CMAF when being designed. I think that's it. Thank you.
Thank you. The fourth paper is LiveClip towards intelligent mobile short-form video streaming with deep reinforcement learning. Should be presented by Jianchao He from Sun Yat-sen University. Zhenchao, please.
Okay, can you hear me now?
Yes, please go ahead.
Okay. Hello, everyone. We are from Sun Yat-sen University in China, and I am the presenter of our paper, LiveClip towards intelligent mobile short-form video streaming with deep reinforcement learning. As everyone knows, mobile short-form video sharing is becoming more and more popular in recent years. However, there remain some challenges. First, rebuffering may happen from time to time. So it is annoying as the video is only of several seconds. And if more content is buffered for this video, then it means less resource for the future videos. Also, a user may switch to the next video at any time. And we also need to consider the data cost when a user is using cellular network. So we need to balance users' viewing quality and the extra data cost. And so we conduct a measurement study on Douyin. This is a very popular mobile short-form video sharing app in China. And we find that there are many differences between the traditional video sites and the mobile app. Here, video streaming is heavily driven by user gestures, and the strategy adopted causes degraded viewing experience and lots of extra data cost. We collect videos from the app and analyze their distributions of bitrate, video length, and so on, and use them as a video data set for evaluations. And then we propose LiveClip to generate streaming policy in real time. We take the bandwidth, the user scrolling events, and the player states as input, and take which videos to be downloaded at each time slot as the output. And luckily, the evaluation results show that LiveClip is doing better than the existing fixed methods. So that's the brief introduction of our work, and thank you.
Thank you. The last paper in this session is what you see is what you get. Measure ABR video streaming QoE via on-device screen recording. It should be presented by Shichang Xu from Google. Please go ahead, Shichang.
Hi, everyone. I'm Shichang Xu. This is a work when I was a graduate student at the University of Michigan. So the background of the work is that, so as we know, mobile video streaming traffic has been grown tremendously in recent years. And to deliver good QoE over viable network conditions, ABR streaming or adaptive bitrate streaming has been adopted widely. So the key idea is that on the server side, the videos are encoded into different tracks with different quality levels. And during the playback, the player can dynamically select which track to play based on the network conditions. And for a lot of entities, it is very essential to monitor the delivered quality of experience or QoE. Some common QoE metrics includes what tracks are being displayed. So that means what video quality are displayed to the users, whether there are stalls during the playback. However, for most third-party entities, it is very challenging to get such QoE information in practice, as the commercial streaming services are typically closed-sourced proprietary services that do not typically expose such information. To address this problem, so for many third-party entities, what they typically do is they will perform their own active testing. So they will use their own test mobile devices to stream test videos in different locations of the network, and then analyze the network traffic to infer the video QoE. But one problem with that is nowadays end-to-end encryption protocols such as HTTPS and QUIC are increasingly adopted, making it very challenging to analyze the network traffic. So in this paper, we explore a very different approach to QoE measurement. We utilize the screen recording capability available on the device and record the screen display during the video playback. And later we analyze the recorded video to measure the delivered QoE. We perform measurements and identify various challenges involved in this process. So for example, we identify that during the screen recording process, there can be significant distortions introduced in the recorded video. So based on these measurements, we develop techniques to accurately measure video QoE despite these distortions. So the QoE information we can get includes the store occurrence, as well as displayed track information across time. We perform extensive evaluations and demonstrate that we can achieve very high accuracy, even in the presence of such recording distortions. If you are interested in our work, welcome to check out our paper for more details. Thanks.
Thank you. So now let me switch to the questions. Okay, I try to go each paper one by one. So this is the question for the paper number 1, self-play reinforcement learning. So the first question is, what do you think using PPO brings compared to the now usual A3C SRL approach? Tianqi, can you please answer the question? I think he can't unmute himself.
Okay, thank you.
Okay.
Okay. Yeah. Yes, indeed, PPO can achieve higher sample efficiency compared with just like A2C and A3C algorithm. And moreover, we have reproduced pensive using PPO method and find that the learn policy actually improves almost 5% on average QoE compared with the original pensive model. So I think PPO can achieve the better performance and can achieve the higher sample efficiency compared with A3C. So thank you.
Okay. The second question is actually by myself. Can you explain a little bit of details of the neural network architecture and how long does it take to train the neural network, or can it be trained fast enough for real-time usage?
Okay, it's a very good question. So we know that we use different neural network architecture for different scenarios, or I can say different tasks. And in our paper, we compared different network architecture in the ABR scenarios, and results show that we can use a very simple neural network representation. For example, use only 3 fully collected layers, which is sized 188, 128, 64, and 64 respectively, to represent the feature extraction layer. So, and it makes sense, it makes sense since the ABR is a lightweighted task, so which can be solved in a practical and uncomplicated manner instead of a complicated neural network. Yeah, and in terms of the real-time usage, actually, currently SWI is not so sample efficiency. So, and it may be our future work. Thank you.
Thank you. Okay, so the first question is by myself. Can the proposed method work well also on scenarios other than IFEC considered in the paper?
Yes, for sure. So the idea of this scenario was motivated by an use case of 5E Essence, which was a H2020 project, where there was a company with the need and the real commercial interest on this wireless scenario for the systems. And it was also interesting in order to consider quality of experience fairness, since in this scenario, all the passengers have the same devices and they have more or less the same coverage. So you will complain if you have a bad quality compared to the person which is in front of you. So you're paying for the same service. But in any case, it can be applied to other dense scenarios like trains or maybe stadiums or conferences. So in general, in cases where we have a high density of clients and access points covering them in order to apply this load balancing of our solution, and also where mobility is not so high to have very frequent disconnections or uncontrolled handovers. Yes, that's the idea.
Okay. The next question, how scalable is your solution? What is the impact on exchanged control message on QoE? Can you briefly answer the question, please?
Okay, so regarding the algorithm, we thought that we think that it is very scalable. We have simulated up to 100 of users, dozens of access points and qualities per video, and we obtained in general solutions in less than 1 second. So I think it's pretty good. And regarding the control messages, we haven't focused on this right now, but in principle, in cases where mobility or the users are not changing the movies all the time, we don't expect a high impact of these messages to recommend rates and move the users.
Okay, thank you. Let's go to the paper number 3. Okay, so the first question is, can you please elaborate on your simulation model briefly? Can you unmute yourself now? Yeah, okay.
Oh, can you hear me now?
Yes.
Okay. Sure. So the simulation model was developed in NS3. It was based on an already existing model of Dash in NS3, and we have extended it to support CMAF chunks, traffic shaping, more accurate logging of buffer level, latency, as well by implementing more ABRs. And the reason why we chose NS3 is because it's highly extensible. So you can, for example, try Dash model or CMAF model in with Quick, which is a hot topic right now as well, or different transport protocols, or Wi-Fi networks. I hope that answers the question.
Yeah. Okay, the next question is, in how far is it realistic to use buffer-based algorithms such as BOLA for LL streaming, where the buffer will never exceed the short target delay, let's say 2 seconds?
So I suppose it all depends on the segment duration and chunk duration in terms of CMAF. So if the segments are 2 seconds, but the chunk duration is, for example, only 100 milliseconds, then it would be very realistic to use it. So I guess it's tied to the segment duration, chunk duration.
Okay. Let's move on to the paper number 4, LiveClip. So Jian Chao, please unmute yourself now. I guess you can do that now.
Okay.
So the question is, if I understand, the user state is considered to be the series of past retention times of previous videos. How can semantic info on the video content be incorporated in the scheme?
Okay. Actually, the state includes the series of past bandwidth, past retention time, and something about the player properties. And as for the semantic info, I think we can divide the videos into different categories like sports videos, daily videos, and so on. And we can add that category info to the state space as an input. And also we are now working on the video recommendation, and we want to better predict the user retention time and so that we can provide better viewing experience. And that's it.
Okay, thank you. Another question is, can you summarize which part of the proposed method has been designed particularly for short videos? Can the proposed method work also for longer videos, or did you observe any influence of the video length on the performance?
Okay, our method is based on the findings of our measurement, because short videos definitely have shorter length, so they are usually designed to be playlist driven and user gesture driven, and so that we include user retention time into the state space, and we choose which video to download at each time slot as the action. So so that the model is able to choose the action at each time slot in case there is user interaction. And for the second question, I think it should work for longer videos as long as they are also playlist driven and user gesture driven and adopts progressive download. And for the third question, and I observed that in general, the model expects users to stay maybe a little bit longer on longer videos. So if a specific user is very impatient, it may lead to more extra data cost, but that also depends on the hyperparameter settings. So yeah.
Okay, thank you.
Okay.
Let's move on to the next, the last paper. Chang, you can come to the microphone. So, okay. Yes, the first question is, why your solution requires a full reference technique? What is happening if the content is transcoded again at the edge to satisfy network requirements?
That's an excellent question. So the reason why our solution requires a full reference technique is that it is very challenging to analyze QE without a reference. So for example, some movies, some video content might contain a still image. So the image will stay on the screen for a few seconds. If we don't know what's the original video, it's very difficult to tell whether that's a store or is just a still image in the video content. And another example is if we don't have a reference of what each track looks like what track looks like after the encoding, is very challenging to identify which track is being displayed. That's why we adopt a full reference approach. And for the other question, what is happening if the content is transcoded again at the edge? I'm not exactly sure about this question. So from my understanding, I'm not sure what it means to transcode at the edge. Yeah, it would be good to add more context to the question.
Okay, probably Abdelek could put some more details about the question later. Okay, the next question is quite simple, I guess. Is your tool open source? Can I use it?
Yeah, that's a good question. So we are working with AT&T. So AT&T provides an open source tool called AT&T Video Optimizer. So we are working with the AT&T Video Optimizer team to incorporate our tool, so it will be eventually open source. Yeah.
Okay, sounds good. Okay, there are a lot of questions that have not been answered. But for the time constraint, I'd like to invite all the authors to the Slido, and you can continue the discussion and question answering there offline. And I'd like to thank all the authors for the session and answering the questions. Thank you very much. And I'd like to hand over the microphone to Lucille for the second session of NOSSDAV. Lucy, are you ready?
Yes, I'm here. I'm just going to share the screen. All right. Okay, so let's move on to the second session then, which is on immersive media. except for one paper, but we decided to still include it in the session. Okay, so we'll start with the first paper, which is SR 360, boosting 360-degree video streaming with super resolution. This paper is by Jiawen Chen, Miao Hu, Zhenqiao Luo, Zelong Wang, and Di Hu. So Jiawen Chen, you can now present.
Okay. Can you hear me?
Yes, it's fine.
Oh. Hi, I'm Jiawen from Sun Yat-sen University in China. I'm going to talk about my paper SR360, boosting 360-degree video streaming with super resolution. 360-degree videos have gained increasing popularity because it provides users with immersive viewing experience. Given the limited network bandwidth, it is a common approach to only stream video tiles in the user's FOV with high quality. However, the user's QoE heavily depends on available bandwidth resource. Moreover, there are many factors that can influence tile bitrate selection, such as time variant network conditions, head movement orientations, and so on. In this paper, we redesigned the streaming systems by using the technique of super resolution. The basic idea of our work is to utilize abundant computation resources on the user device to trade off a reduction of bandwidth. In our work, a video tile with low resolution can be enhanced to a video tile with high resolution using SR techniques at the client side. We adopt the theory of deep reinforcement learning to jointly make a set of decisions, including user FOV prediction, bitrate allocation, and SR enhancement. By conducting extensive evaluation, SR360 outperforms other methods by at least 30% on average under different QoE metrics. That's the introduction of our work. Thank you.
Thank you. So we'll now move to the second speaker for paper number 2, low latency cloud-based volumetric video streaming using head motion prediction. This paper is by Saran Gul, Dimitri Podborsky, Thomas Buchholz, Thomas Chiel, and Cornelius Helge. So Saran, if you can speak.
Yeah, can you hear me?
Yes, it's fine.
Okay. I'm Saran Gul from front of HHI. I would like to briefly present our paper, low-latency cloud-based volumetric video streaming using head motion prediction. It's a joint work of front of HHI and Deutsche Telekom. So first, a few words on volumetric video. Volumetric video provides a highly realistic 3D representation of an object and allows the user to freely navigate in the scene and observe an object from any viewpoint. Volumetric content is typically stored as 3D point clouds or textured meshes. And in our system, we consider the streaming of textured meshes. One problem with the streaming of such content is to mobile devices is the huge rendering complexity. So although the devices are quite powerful today, it's still a challenging task to render rich volumetric videos in real time, especially if there are multiple objects present in the scene. And also there are yet no efficient hardware decoders for volumetric data. And software decoding can be very expensive in terms of battery usage, and it also may not meet the real-time requirements. So for this reason, we developed a streaming system where we offload the rendering to a powerful cloud server and transmit a rendered 2D view from the volumetric video based on the head pose of the user. However, this adds a certain network delay and also processing delay due to the rendering and encoding on server side, which increases the interaction latency, which may degrade the user experience. So for this reason, we have several optimizations in our system. For example, we use GPU-based encoding using an NVIDIA codec, and we use WebRTC for low latency streaming. And also the focus of this paper, we use head pose prediction methods to predict the head position orientation of the user so that we can proactively render a view from the volumetric video corresponding to the future head pose of the user. So this can eliminate a large part of the interaction latency and make the application more responsive. But the accuracy of such algorithms is very important because mispredictions can cause various artifacts and also make the objects appear unstable in the scene. So to mitigate this, we developed a predictor based on a simple auto-regression technique in our paper. And yeah, we collected user traces to train models for our predictor and evaluated the performance of the predictor for a prediction time between 20 to 100 milliseconds. And yeah, in the paper, we show that our approach performs better than a baseline approach where no prediction is performed. Yeah, and in the future work, we want to look into the subjective effects of latency and prediction errors on user experience. Thank you.
Thank you. So we'll move on to the third paper, which is Viewport Prediction for 360-degree videos, a clustering approach by Afshin Tagavi Nasrabadi, Alishan Samie, and Ravi Prakash. So Ravi, if you can unmute, if you can speak now.
Yes,
Okay.
thank you, Lucille. This is, and thank you everybody. This is a joint work with my former PhD student Afshin Tagavi and current student Ali Hassan. And as you've already have had chance to view the 15-minute and 3-minute videos, this will be more loosely paced. The main takeaway here is that if on the server side, user head movement could be tracked from past viewing experiences of viewers of the same video, then using something called a closeness fit, which is basically how far apart the centers of the viewport of the past viewers are, past viewers of a given video could be clustered. And then if they could be clustered, and then a new viewer comes in, based on where that new viewer is looking, we could basically try to place that viewer in a given cluster. And if the new viewer corresponds to a given cluster, then the viewing behavior of previous viewers in the same cluster could be used to predict the viewport of this new viewer. And if a viewer cannot be placed in any cluster, then a fallback mechanism like last viewport or something else could be used for that viewer. So that's the whole idea, that use offline calculation of past viewing behavior of previous viewers and couple that with the online behavior of the current viewer. And we've compared that with other approaches. And of course, the main takeaway is that for some videos where with very distinct region of interest, this solution works quite well. We'll be the first ones to admit that it doesn't work very well for all kinds of videos. It's much dependent on the nature of the video, especially videos with very strong motion component in a given direction that tend to attract people's views towards a few objects. It really works very well. So that is a very quick summary of our work.
Okay, thank you very much. Okay, so our fourth speaker is Mohammad Hoke. Yet I don't know if he's here. In case Mohammad, you're here, not sure. Okay, so let's move on to the fifth paper, and maybe Mohammad will be able to come back a bit later. So our fifth paper is PC MCU, Point Cloud Multi-Point Control Unit for Multi-User Holo Conferencing Systems. And this paper is going to be briefly presented by Gianluca Cernigliaro, Mark Martos, Mario Montagu, Amir Ansari, and Sergi Fernandez. So Gianluca, can you speak? Yes, we can hear you.
And you can also see me, I guess. So thank you very much for the presentation. I will start. So in this work, we designed a holographic conferencing component called the Point Cloud Multi-Point Control Unit, or Point Cloud MCU. So the goal of the Point Cloud MCU is to be for holo conferencing what a traditional MCU is for video conferencing, and of course also to become a key component for multi-user holo conferencing systems. The reasons behind this idea are the increasing popularity of holoportation and also the fact that they are real-time transmissions of volumetric video. So we thought that they need a specific component for that. And it would be crucial to have it in a server and able to optimizing the communication between users that are represented as holograms, and in this case as point clouds. So as I said, the idea is based on the traditional MCU for video conferencing. And with the point cloud MCU, we aim at reducing at the end user side, at the user client, the computational resources and the bandwidth usage. This reduction is provided by a set of functionalities that are implemented in the point cloud MCU. The first one is the fusion of volumetric videos belonging to 2 or more remote users. So they are geometrically fused within the space, depending on the holographic conferencing environment. The level of detail adjustment, which is done to optimize the volumetric video resolution based on the user's relative positions. And the last one is the removal of non-visible data, so that the content that is not placed within the user viewport is never received because it's not needed. So the results that we are presenting in this paper show that introducing the point cloud MCU in our conferencing system, we are able to reduce the computational resources usage, and also in terms of data occupation, saving the bandwidth. These results are obtained comparing against a holo conferencing system without any optimization component. So apart from proving this, the paper wants also to be a starting point to open the door to further research, to enable this kind of scalable concept to the holo conferencing, and to allow the participants to reduce the computational power needed to receive this kind of data. That's it. Thank you very much.
Thank you very much. So, okay, I cannot find the speaker for the fourth paper. In case, Mohammed, you're here, you can just try to talk. Otherwise, we'll move on to the questions. Okay. So let me change and move on to the Slido. Okay, so we'll start with the first paper, which is, so that was Jawen. So the most trendy question here is performance of SR360 limited to lower bit rates like other SR methods? Jawen, if you can talk.
Oh, okay.
Yes.
Can you hear me?
Yes, we can hear.
Yes. Yeah. We utilize abundant computation resources on the user device to trade off a reduction of bandwidth. So the video with lower bit rates can be enhanced to a higher bit rate. But when the video bit rates are closer to the highest bit rates, it will get relatively less enhancement.
Okay. So we have another question, which is more or less also similar to the third one, which is which quality of experience metrics you use to compare your work with the other methods? So did you use the same QE function for all the streaming logics you compared with?
Okay. Yes, we use the same QoE function for all methods. The QoE function includes 3 items: the average viewport quality, the penalty of rebuffering time, and the average viewport quality change. For those methods without using SR, the perceived bitrate is not enhanced, and the processing time taken by SR model is non-correspondingly. So the QoE function is general for all streaming methods. And we use the parameter settings is the same as another paper called DRL 360. Okay, thank you.
Thank you. And maybe a very last question on this one. So maybe Jung-Suk's question: when the video is compressed to low quality, the compression artifacts may become even stronger by super resolution. Can you comment on the interplay between the compression and SR in the proposed method?
Okay, in our work, we built an independent SR model for each video, so we can achieve near zero training error due to the inherent overfitting property of DNN. It can learn the features that map the low resolution video to the high resolution video. This content-aware SR can be seen as a type of video compression over the entire video. Okay, thank you.
Thank you. So let's now move on to the next paper. So for the next paper, we have also a few questions. So Sarah, if you're able to speak now.
Yes.
So I'll start with the first one, which is how much were the minimum and maximum end-to-end delays of your method?
Okay, so we considered the range of 20 to 100 milliseconds, and this was determined based on our motion to photon latency measurements, and we observed an average of 60 milliseconds, and we set the range appropriately according to that.
Okay. And maybe another one. So can the prediction models for head motion be generalized to different scenarios, or are they specific to simple and selected scenarios?
Yeah, I think this is a very good question. So in our experiments, we didn't instruct users to follow a specific pattern. So we just showed them the objects and instructed them to view the object freely, look from different angles. So in this sense, I think the methods are pretty generalizable, but how good you can predict it, it probably depends on how static and dynamic the objects are and how fast the user is moving around, so, of course, like how fast the head pose, the position orientation is changing. So it's the predictability is, it depends on the head position speed, head movement speed. Yeah.
Okay, thank you very much. So as we are a bit late, we are going to stop here for the questions related to this paper, but please go on Slido and answer the remaining questions that are also very, very interesting. So let's now move to the third paper. Okay, so Ravi must be here.
Yes, I'm here.
Yes, Ravi? Okay.
Yes.
So let's start with the first question here. Is it possible to control the number of clusters? And if yes, what would be the effect of the number of clusters on the performance? As an extreme, what if the nearest neighbor is used without clustering?
Yes, it is possible to control the number of clusters. In our paper, we describe this notion of closeness. So the whole idea is that we cluster nodes based users based on how close their center of viewport is with respect to each other, as with regard to the distance on the great circle. And so if we reduce the amount by which they have to be close, so we form tighter clusters, there could be more clusters. On the other hand, we could have looser clusters where viewers that have been farther apart in the future could be clustered together. So that is possible. Now, if we form very tight clusters, there could be many more clusters. And then if a new viewer can be mapped onto a given cluster, the prediction accuracy would be higher. But then, of course, there'd be a large amount of fragmentation in clustering.
Okay, thank you. So maybe another trendy question here. Why not to take into account motion behavior or video content?
Yeah, that's actually a very good question. And that's something that we've been considering. Here is the problem. If we look at this work, we have tried to predict viewport based on user behavior, not on trying to understand the semantics of the video, because that's a whole different area of investigation, trying to understand the meaning of the video. Now, what we have observed is indeed that videos with very strong motion component do tend to attract viewers in a given direction, and prediction accuracy is higher. So yes, this work could be combined with ideas of, say, detecting saliency and detecting motion vectors and those kinds of things. So you could take a cluster and say if this whole cluster is tracking the same moving object, then there will be a higher level of prediction. So that could definitely be done.
Okay, thank you very much. So the same here. We'll stop and please go on Slido to keep answering the questions. So
Thank you.
I'll now move to the 5th paper. So Gianluca, can you talk?
Hello, yes.
Yes, okay, very good. So let's start with maybe a first question. So the PCMCU fuses the representations of the different participants. How is that done?
So this is basically a simple geometrical fusion. So imagine that you have 2 point clouds received by 2 users. You are the third user. Each point cloud has its own system, geometrical system reference, but there is a different one in the client device of the person who is going to have the two represented at different relative positions. So the point cloud MCU knows the position and put them together in the same geometrical world, basically, and they are compressed and transmitted together as only one point cloud.
Okay, thank you. So let's have a second question here from Karsten. Since you are proposing a conference system, is dash style segment streaming ideal, and doesn't the delay get more noticeable as immersion improves?
This is actually a very good question, and basically what we are using here is a work done in collaboration with other partners of a European project. And actually this work has been presented a few days ago by our colleague Jack Jansen, which I think is in this call right now. And we have prepared a dash transmission system purposely created for low latency point cloud transmission. So this is what you're using. Of course, we are using this because it's part of the scope of our work. But in theory, the idea behind the point cloud MCU is to have it ready to use any transmission system that is going to be the standard at some point for point cloud transmissions.
Okay, thank you very much. So we are going to stop here for the questions. I'm doing a very last try. Mohammad Hoki, are you maybe here somewhere as another name? No, I don't think so. Okay, so let's give up then. So thank you very much to all the authors of this session and of NOSSDAV more in general. Thanks also a lot to the fantastic audience. We got very numerous questions, so that was really exciting. And it would be very, very nice if the authors go on Slido in the next hours, next few days to keep answering the question they get on the papers. So thank you very much, all of you, for having attended NOSSDAV. And I now can hand over to maybe Laura.